Okay guys, this video is going to be about DC motors and some generator stuff here. I don't expect you to understand everything, remember everything, but I do want you to know the basics of what these slides tell you. These are important for many reasons, especially for this alternative energy, since most of your devices have motors in them, and those are the ones that we really have to be careful when we're applying energy to them, or voltage, current, whatever. So anyway, let's start out here. We're talking about DC motors for this series and generators for this series of videos. There should be about 3, so this is part 1. Okay, if you look on the screen, you'll see that you've got 4. Actually, let me go back here. Actually, 1, 2, 3, 4, 5, 6 different connections for motors. Okay, now the first part of this video is going to be what's called permanent magnet DC motors. Okay, and so by permanent magnet, what we mean is the motor has a permanent magnet that generates a field, and then you have the armature where current goes into it to cause the motor to rotate. Now, if it's a generator, then the armature is what's generating the output current and voltage. Okay, so here in this first drawing here, essentially this shunt winding here would not exist if it was a permanent magnet motor, and so what you would have is just the armature winding here, the armature here, and you'd have a permanent magnet which generated a magnetic field, and the armature is rotating inside the magnetic field that's generated there. So anyway, that's permanent magnet. Now, those are called permanent magnet motors and generators. But there's also wound motors, okay? And by wound motors, that means that you have a coil of wire that's actually generating the field, okay? And so here we have what's called a shunt connection. So you have a coil that's actually electrically hooked in parallel, and that's what shunt means, in parallel with the armature of the motor. Okay, and so basically what happens is this is the field current, and this is the armature current, and then this is the output current going through here. So this is a shunt type connection. This is a series connection. So here your field winding is in series with the armature. Okay, so this is a series. So armature in series, and this drawing here includes an inductance and also a resistance. So every time you see this symbol here, this is the armature. It basically has a resistance and inductance. Okay, that's inside there. So the armature coil. All right. So this is the series connection, and here is called a cumulative compound. So notice that what happens here is you have a winding for the field that's in parallel or shunt with the armature, but you also have a winding that's in series. So that's why it's called a compound, because it incorporates both this and this. Now the construction is different, and we can talk about that another day, but essentially this is the way the windings are arranged, and this is called a differential compound. And so notice here that what you have is you have essentially a series connection in shunt or parallel with essentially this connection. So it's a differential. And then here what we have is called a long shunt, and basically what you see here is you got the field winding and then a series winding here. And so that's your F and your S, so the S is in series and the F is basically in shunt. So here you got a series winding in parallel with the shunt winding. And then you have a shunt short. Let's see, this one looks kind of like this one here. So we'll talk about that one later. So basically the main ones to remember here are the shunt, the series, and the compounds here. Okay. All right. So there's what we're talking about when we're talking about DC machines, and it could be motors or generators. All right, let's go to the next slide. Okay, so here PM, so this is permanent magnet, so that means that you don't have, it's not a wound type motor. That means that you have a permanent magnet that's generating the field winding, field, and electromagnetic field, and then you have the armature. Okay, so the schematic of this, notice that all you're showing is the armature circuit because the permanent magnet is generating the magnetic field, and basically here is where the armature is, and you have a resistance associated with the armature winding, and you also have something that's called the counter EMF. This is actually acts like a voltage source. Whenever the motor starts to rotate, this generates a voltage, and this voltage tends to oppose the voltage that you're applying. So this would be a plus polarity here for the VA, the applied voltage, and then this would be a plus for this. So you can see is actually opposing that. And what happens is when you first start up your permanent magnet motor, then basically this right here is not rotating, and so the only thing you have reducing the current is the armature resistance. So it's a large current to start with. But as the motor starts to rotate, then this creates a voltage, and this voltage tends to oppose this, and so now the voltage across the armature resistance is this voltage here minus the voltage generated across there, and so as a result you have less current. So the faster this rotates, then the less current that's actually flowing in the motor. Okay, so let's start out with some equations. So V is VA is the applied voltage, IA is the current that's flowing into the circuit, and RA is the armature resistance, and KE represents the voltage generated by the motor in the armature circuit. Okay, and this is often called the counter EMF. It's because you've got the windings of the armature coil, and basically as they're rotating in the field, magnetic field, what happens is a voltage is generated in here, and basically it opposes this voltage here. So that's called KE omega. Omega is the speed of the motor, and KE is the electrical motor constant. Now here what I'm doing is solving for the armature current, and so what we have is the armature current is equal to the applied voltage minus this voltage induced in the armature, okay, divided by the armature resistance. Okay, and so that's the armature current. Now for all motors, the torque is proportional or dependent upon the current flowing through the armature here. So the torque can be calculated by multiplying the torque constant, KT, times the actual current flowing in the armature. So here what I've done is taken this equation here and multiplied everything by KT, and so what we end up with is KT times the voltage applied divided by the armature resistance times the product of the torque and electrical constants times the speed, the rotational speed. In this particular case here, we're talking about radians per second, okay? And then here's divided by RA. Now, if I go in and I break this off into the parts that are constants and the parts that are varying, you notice that KT and RA are fixed. The armature resistance is fixed, and the voltage applied is fixed. Also, the torque constants are fixed, and this is fixed. So if I go in and rewrite this and put the things in parentheses that are constant, and I didn't put this, but this is all constant, then you notice that this can be written in this form here, okay? And so I'm letting A represent the insides here, and letting B represent this. So what we have is that the torque is equal to minus some constant times the speed in radians per second plus some other constant. Well, this is a linear equation, okay? So that should be obvious to you, and it should also be obvious that this is the y-intercept, and that this right here is a negative slope, okay? So the slope-intercept formula. So at omega equals 0, okay, it's not rotating, then what you have is the torque is equal to B, and so this is on the intercept, so this is a positive constant. But as the speed increases, then at a negative slope it goes down. So here T max occurs when omega equals 0, and so if we plug that into here, 0 into here, we see that the torque, the maximum torque, occurs when it's not rotating, omega equals 0, and that equals KT VA over RA, which is this right here. So you could plug this 0 into here, so this is gone, it's just that. So that's the maximum torque you can get. Because notice what happens is the speed increases, then what happens is this right here is a negative number that's added to that, so it reduces it. Okay, so here's another question. What is the maximum speed? Well, we can basically look at this equation here. I've written it down again. And notice if I solve for omega, I get B minus T over A. Okay? So the maximum speed occurs when the torque is equal to 0. Okay? Because how do I know that? Because look, you got B over A and you're subtracting T. So if T is positive and you're subtracting from B, then that means your speed is going to be reduced, right? So if the torque is equal to 0 here, then the maximum speed is going to occur when you have B over A. Now, if I plug in from B up here, this is B, this is B, and this is A. If we plug that into here, then what we end up with is the maximum speed equals the applied voltage, which is the voltage right here, divided by the electrical constant. Okay? So if we go in and draw this curve, torque versus speed, then what we see is when the speed is 0, we have the maximum torque, which is KT VA over RA, and whenever the speed is maximum, we have 0 torque, but we have maximum speed of VA over the electrical constant. Okay? All right, let's go to the next slide. Now here, I'm going to let you read this. I'm just trying to basically go in and explain what's going on here, but let me explain with words. Okay, so here's our torque speed curve, okay, for the motor. All right, omega are the speeds here, torque's locked here, and what I've done is I've drawn a horizontal line to represent a constant torque load. In other words, what this kind of load is it's a load that no matter how fast it's rotating, the actual load torque or the resistive torque is always constant. Okay, it's not varying. You can have torques that increase, you can have torques that decrease or whatever, but here for this example, we're assuming that we have a constant load torque. Okay, so this is the load torque and this is the motor torque. So the question is, what speed will it operate at? Well, it's going to operate at the intersection of these two curves. Okay, so you'll see that at this point here where they intersect, that's going to give you, if you drop this down, this is the actual speed of the load and the motor, and this is going to be the torque that's actually being produced by the motor and by the load. Now, in order for the motor and load to stabilize at a constant speed, you have to have the sum of the torques to be equal to 0. If there's a net torque, then it's going to keep on accelerating. So what this curve is showing you is that at this point the torques are equal, so they cancel each other. So you can think of the motor as a positive torque because it's being produced, and you can think of the load as a negative torque because it's taking away from the motor produced torque. So the net torque is going to be 0. But notice that the motor is still producing this torque and the load is still producing this torque to keep it going, but they're canceling out, so there's no acceleration. You just have a constant speed here, and this is the torque that's being produced by the motor, and this is the torque that's being consumed by the load. Okay, and that's all I'm saying. So initially, let's start from the beginning. So let's say that the motor is stopped. Okay, and so basically, and you have it turned off, and so you go in, you hook a load which has this torque characteristic to the motor. So you turn on the motor. Well, instantaneously what's happening is the motor hasn't started turning yet, but voltage is applied. Okay, so you're creating a torque here by the motor, but this is the torque that the load is consuming. So notice there's a net torque. You got more motor torque being produced than load torque that's being consumed by your load. Okay, so you got a net torque, so it's going to accelerate. Anytime you have a net torque, it's going to accelerate. Okay, so when it accelerates, the motor has to work on this curve here because this is its characteristic. So what's going to happen is basically it accelerates, so now your speed goes up to here, say. Well, when it goes up to here, now what's happening is you're producing less torque, okay, but you have some speed, it's moving. And then you still got a net torque, so it's going to accelerate. And as long as this curve here is above this curve, you're going to have acceleration, okay? Angular acceleration, it's rotating. So it keeps rotating, the speed keeps increasing. But when you reach this point here, the torque produced by the motor equals the torque consumed by the load. And so at this point here, it stops accelerating. And so it stabilizes at this point, and then you have an operating speed here, and you have a torque that's being produced by the motor here, and also the torque's being consumed by the load. Okay? Now here what I do is I basically go in and let's look at power. Okay? So we talked about how it operates and stuff, but let's look at the power that's being produced. Now the power produced by a motor is the torque times the speed. Okay? So torque times the speed. So what I do is I basically go in and take the equation that we had previously, which is, let's see here, right here. Okay, so here's my torque equation here, and I multiply it by the speed, omega. So multiply that by omega, multiply that by omega, and notice this becomes squared. This is a linear term, this is a square term. So if we go back over here and go back, okay, so what happens is then we have the power equation. Okay, so torque times omega is the power equation. Now what I'm going to do, just to make the equation seem more familiar, is I'm going to let this here be C, and I'm going to let this here be D. Okay, so D is just this right here, and C is just this right here. Okay, now if you look at this equation now, you should recognize that this is a quadratic equation, right? Because you got this omega squared term. Now the fact that you got a negative here, what does that tell you? Well, that tells you that the power curve is going to be like a mountain. It's going to look like a mountain, right? It's going to go up and down. If it had been positive, then it would look kind of like a valley, like a U shape, right? But this is a negative, so this quadratic is going to go up to a peak and then come down. So the fact that it looks like that should tell you what? Well, it should tell you that there's some speed where you're going to be extracting the maximum power from this motor, and that's something of interest. Okay, so anyway, this is the power equation, this is C, and this is D. So let's go to the next page. All right, go up to the top here. So wow, there's my power curve. So here's the torque speed, and here's the power curve. Okay, now this equation has torque for the vertical axis, but the power equation has power, and so I should have probably drawn a vertical line here for power, but this is the peak power. So at this speed, which I'm calling omega the motor peak, and then torque motor peak, produces the maximum power here. Okay, now this should remind you of some of the stuff we were doing earlier in the course when we were talking about the power being extracted from what? Well, from a solar cell, right? We had maximum power point and maximum current point, you know. So anyway, it's you're going to find this a lot in engineering and technology. You see things that you learn in one subject that look just like things you're doing in another subject. Okay, so anyway, this is torque and speed for maximum power transfer. So what we want to do is we want to find out what maximum speed, or what speed and what torque produce the maximum power for this. So under what conditions can you extract the maximum power out of this motor? Okay, so what we do is we use a little bit of calculus. Now notice the maximum point, if you look at the slope of this curve, well, the slope of this curve is positive here, and the slope of the curve is negative here, but the slope of the curve is 0 here. So it starts with a positive slope, and it's getting less positive, then 0 slope, and then here negative slope, and more negative slope. So the maximum occurs when the slope is 0 for this particular case. And that's true in general. You have a maximum or a relative maximum when your slope is 0, or something called an inflection point. But here, for this simple curve, the maximum occurs when the slope is 0. So using some simple calculus, you can go in and take the derivative of this, okay, which is the instantaneous slope of this curve. And so I'm representing that by dp over d omega. So when that's 0, then if I take the derivative of this, then basically the derivative will just leave this constant, get rid of this, and it will take this second order, or power 2, and make it a 1 power, and multiply the 2 times that. So what I end up with is this equation here, okay? And so if I basically go in and solve for maximum power point, what I see is the maximum speed, or the speed at the maximum power output, equals c over 2d. Now if I plug in the values for c and d from the other slide, then I end up with this right here. This is c, 2 times d, and I find out that the speed at the maximum power transfer occurs for a value of VA over 2 times KE. Okay, so that's what this speed is. That's the speed when I have maximum power transfer, right here. Okay, now my question is, well, I know what this speed is. What is the actual torque that's being produced at that point? Okay, and so that's what we want to do now. So what I do is I go in and take my torque equation that I had before, and I plug in this particular speed into the equation, and I end up with this, and I end up with this, and what I see is that it's equal to 1/2 kT VA over RA. Okay, so if I go in and look at maximum power that's available from this motor, okay, is I see that what we have is when we multiply the torque, the maximum torque, or the torque at maximum power transfer, the speed at maximum power transfer, and multiply it out, I end up with this equation. Now, this is something you guys have seen before. You saw this when we were doing radio communications, and we had a source with an internal impedance, and we wanted to know what load resistance we could attach to that generator and get maximum power output. And it was always the voltage of the source squared divided by 4 times the internal resistance of the source. Okay, so this is the maximum power that we can get from this particular motor. Okay, so if we go back, let's go back to the original slide here. Go right here. Okay, and we go up the top, then you've got this motor here, and we want to know what's the maximum power that we can extract or available for this motor. Well, it's just equal to VA squared divided by 4 times RA. Okay, and this is the same thing that we did in our radio communications when we wanted to figure out how much power we could extract, and we also did it in our electrical powers course, systems course. Okay, Alright, so this is pretty much it for this first video. That's about 25 minutes. Okay, so this is the end of part 1.